Let me start with a short introduction. So, welcome to the physics colloquium of the Institute of Physics. So it's really my pleasure to introduce Shiraz Minwalla. So Shiraz obtained his PhD in 2000 from Princeton University under the supervision of Nati Seiberg. Then he moved to Harvard, I believe until 2006. I'm not sure exactly which year he moved. And then he moved back to India, to Mumbai, to the Tata Institute of Fundamental Research, where he has been since then basically helping create a new generation of great theoretical physicists from India. And well, Shiraz is extremely well-known leading figure in string theory with many important contributions. He also has won many awards, among which the New Horizons in Physics Prize for his pioneering contributions to the study of string theory and quantum field theory, and in particular, his work on the connection between the equations of fluid dynamics and the Einstein's equations of general relativity. Shiraz is also an extraordinary speaker, and I very much look forward for his talk today. So Shiraz, the screen is yours.
Thank you very much, Joe. Thank you for the over-flattering introduction. Hard to live up to. Okay. So my talk today is titled "The Search for Quantum Gravity," and I will follow roughly the following outline. I will spend some time explaining what I mean by the words in my title. What does the question mean? What do I mean by the search for quantum gravity? I will then talk very briefly, or almost not at all, about the string framework, and then jump to describing, and this is one of the main parts of my talk, a particular successful attempt to create a theory of quantum gravity, a theory with quantum spacetime. I will then spend a little time explaining one sort of interesting outgrowth of this development. The outgrowth being that gravity has become in some ways a theory that has begun to find applications in non-gravitational theories. And then I will end with some future outlooks and conclusions. Okay, so let's start. As almost everyone in this audience knows, over the last 100 years or so, maybe 200, 300 years or so, theoretical physicists have developed increasingly sophisticated mathematical models that now describe a remarkably wide variety of physical phenomena. Okay, so we can model, I don't know, quasars in distant galaxies. We can model semiconductors in labs, and so on. Just very different phenomena, several different phenomena. We have good mathematical models for all of them. Now, something that I find completely remarkable is the following. Each phenomenon is not quite on its own trip. There is a certain unity in the framework of the structures of physics, and that reflects itself in the fact that there are a few fundamental, a handful of basic frameworks. And by framework, what I mean is a mathematical structure and a related interpretive framework associated with that. That there's a handful of such frameworks that underlie the mathematical models that describe all these astoundingly wide variety of phenomena that physics has been able to model. Now, two of these frameworks that will play the central role in my talk are the quantum framework, the framework of quantum mechanics that was developed between 1900 and 1930. And second, the framework of gravity, or the general relativistic framework. So let's start with describing the quantum framework. The quantum framework of quantum mechanics, and in particular, and this is going to be important to my talk, is the framework that has been used in the construction of all models of particle physics over the last 80 years or so. So let me say this in a little more detail. Modern theories of elementary particle physics are set within the framework of what is called quantum field theory. So what is quantum field theory? Well, for the purposes of my talk, I'm going to tell you only very little that will be relevant. The first thing to know about a quantum field theory is that quantum field theories are set on a given background space-time. Okay, so space-time forms an unmoving grid, a sort of stage that is once and for all specified, and this is a stage on which dynamics happens. Okay, space-time is a grid on which things happen within quantum field theory. It's not a participant in the dynamics of the quantum field theory. Now, once we have the stage, we've got space and time, and a quantum field theory is a theory in which you have one or a finite number of degrees of freedom at each point in space. These degrees of freedom sort of evolve in time, and they interact with neighboring degrees of freedom. The interactions in a quantum field theory are local. That is, degrees of freedom interact with the other degrees in their neighborhood, and with degrees of freedom far away, only through the interaction with other things, in sort of waves. Okay, this is all I'm going to say about the structure of quantum field theory for my talk. Okay, in contrast to quantum field theory, which was the framework within which all modern theories of elementary particle physics are set, modern theories of cosmology, the theory of the evolution of the universe as a whole, is set within another framework, the framework of the classical general theory of relativity. So I'm going to give you 2 minutes about this framework. Within this framework, space-time is dynamical. More precisely, the geometry of space-time, the metric on the space-time manifold, is a dynamical variable. Okay. Now, in this theory, just like in a quantum field theory, each point in space hosts a few finite number of degrees of freedom. Okay. And these degrees of freedom continue to interact with each other locally. They also evolve in time. All this is the same as quantum field theory. The big difference between the theories of general relativity and quantum field theory is that these degrees of freedom in the general relativistic theory are classical degrees of freedom. They're just numbers, okay? They're not operators in a Hilbert space like in the quantum field theory. They're numbers. And the evolution is described just by classical differential equations. Okay. So we've learned about we've learned some things about quantum field theory and some things about the general theory of relativity. Of course, most of you know much what I'm saying anyway. Now, you see, quantum field theory has been the framework, as I indicated, that has been spectacularly successful in describing subatomic scale physics, particle physics, the physics of the fundamental constituents of the universe, among many other things. It also describes some other things. Okay? The success of quantum field theory is, of course, famous. Predictions within quantum electrodynamics, a particular quantum field theory, which we'll hear more about as we go along, have been made to many places of decimal, as has been indicated in the slide in this transparency. On the other hand, the general theory of relativity has been spectacularly successful in describing astrophysical and cosmological dynamics from a scale ranging from kilometers to the size of the universe. The general theory of relativity, as I've tried to indicate, has been the framework in which the dynamics of the universe as a whole has been modeled extremely successfully. It's also used to model planetary motion. It's used to get GPS results right. It has a wide range of applicability, but by and large, applicability on large scales, human-sized scales, not scales, human or more than human-sized scales, but not the scales of the very small. However, and this is an important thing, as you have seen from my description of these two frameworks, neither of them is completely satisfactory. Each of these frameworks ignore an aspect of reality but we know to be true. Quantum field theories ignore the fact that space-time, or more precisely the geometry of space-time, is not fixed once and for all, but it's dynamical. This is something that the general theory of relativity takes into account. and when I was describing what a quantum field theory was, I told you that quantum field theory happens on a fixed background spacetime. In the theory of general relativity, the geometry of spacetime is not fixed. It reacts to what's happening and influences what's happening. It's a participant in the dynamics of the universe. This element of reality we know to be true because of the success of general relativity in modeling several phenomena, for instance, cosmological phenomena. That success is based on the fact that it accounts for the fact that the geometry of space-time is dynamical. It participates in the dynamics of the universe. On the other hand, general relativity, which takes this feature into account, ignores something else. It ignores the fact that the basic variables of the universe, the basic variables that live at each point in space, in actual fact are not classical numbers, but are quantum variables. The variables which fluctuate, which have amplitudes, they're operators in a Hilbert space. General relativity ignores this fact. This also we know to be true because of the success of quantum mechanics in describing, well, zillions of things over the last 100 years. Okay, so neither the quantum field theory based framework nor the general relativistic framework is satisfactory for describing any phenomenon in which two things are true. A, that it's important for that phenomenon that space-time is dynamical, the geometry of space-time is dynamical, and B, that it's important that the quantum fluctuations, especially quantum fluctuations of space-time, are also important. If both these things are true in a phenomenon, neither the general relativistic framework nor the quantum field theory-based framework is appropriate for modeling that phenomenon, because each of these two frameworks ignores one of these aspects, which we've assumed is crucial for the phenomenon under consideration. Now, some of you are thinking that's all very well, but what are these phenomena? What are these phenomena that I would want to know about, in which both space-time is dynamical, as well as quantum mechanics of this dynamical space-time is important? Well, to some people, to people of a certain taste, that question is not, it's not necessary to answer the question. Just the fact that quantum field theory ignores something that we know to be true in reality. General relativity ignores something else that we know to be true in reality, tells us that our framework, that we don't have a complete framework for all possible phenomena, and that's enough to motivate some physicists to search for something more. However, more practically minded physicists could ask the question we posed ourselves. And that's sometimes a wise thing to do, unless you can give an example of a phenomenon. Maybe you're tilting at windmills, maybe you're chasing something that you're not totally sure you've got a clearly defined goal. Well, there is at least one phenomenon in which the fact that space-time is both dynamical and that quantum mechanics is important, plausibly in fluctuations of that space-time, there's at least one phenomenon that I think everyone in this audience, as well as most people on planet Earth, would agree is an interesting phenomenon to study. And that phenomenon is the birth of the universe. So I'm going to take 5 minutes to say this a little more clearly and to motivate it, just in case you feel you want a very clear reason to engage in the study I'm going to describe to you. As you know, the general relativity-based model of cosmology has been used to run the history of the universe backwards. This is one of these fantastic things about physics, right? Physics, in its essence, is a set of equations that allow you to take the present and use them to predict the future. But the equations of motion of physics are as good at taking the present and using the present to post-dict the past, to study history rather than predictions. And that's sometimes very useful, because sometimes you want to know your history. And one question that is of interest to us, to all of us as physicists, but also all of us as human beings, is this question that humans probably asked, from the time they could ask questions, which is, how did it all begin? Where did we all come from? Okay. Remarkably enough, we have developed our physics is well enough developed so that we're able to put equations to this question. So we're able to answer this question with equations to some extent. And how we do this, as you know, but let me remind you, is as follows. We use observations to see what the universe is like today. This gives us a cut of the universe at a constant, time slice, or more precisely, a constant light sheet, constant null time slice. Okay, we use our observations as initial conditions and then put them into the equations of the general relativity-based equations of cosmology. And then use these equations to run the movie backwards. Okay, so this is what physics is built for. It takes an initial condition, then the equations allow you to develop to see what things would happen, what would happen in the future, or also equally well what happened in the past. So we can use this to see what happened in the past. So now we take what we see now, we put them into the equations of general relativity, and imagine that we use that to construct a movie about how the universe evolved in backward time. So in forward time, as all of you know, the galaxies are expanding away from each other. We take the initial conditions that we see, put them into these equations of general relativity, and create this backward time movie. And in backward time, we see the galaxies all coming towards each other. And these galaxies all come towards each other. Everything seems to come towards everything else until we reach a time, some 13.6, 13.7, 13.8, something like that, billion years ago, in which things begin to get really interesting. Everything has come very near to everything else. Energy densities are now very high. MeV, TeV, high energy densities. Distance scales are very small. It looks like we're getting close to the beginning of the universe, the stuff that started it all. And now you might ask, what happened before that? And the answer is, we don't know. And the reason we don't know is that the equations that we use to run the movie backwards fails at some point because of our ignorance. To go further back, to answer what happened before this intensely interesting time where things came very close to each other and everything's very dense and very interesting, we know we need better equations, and plausibly, it's not clear, but plausibly the equations of quantum gravity. So at least plausibly, and we won't know this for sure until we know the answer, but plausibly, in order to answer this question that people have asked for forever, how did the universe begin? We need to do better than the quantum field theory-based framework and the general relativity-based frameworks that we have. We need to somehow put them together and find a framework for quantum gravity. Okay, so this is my offering for why this study of quantum gravity is an important one. It's important for us to answer the kind of questions that got us studying physics. Okay, great. Now that we're all motivated, we all want to know the theory of quantum gravity. What is the answer? What is the theory of quantum gravity? Well, of course, the answer is we don't know. And why don't we know? There have been a lot of people working on this question for a long time, and yet we don't know the theory of quantum gravity in our universe. Why is it that we don't know? Why has progress been so slow? Well, there are possibly many reasons, but one important one is the following. The quantum fluctuations of space-time geometry are important, qualitatively important, and basically non-negligible, only at very short length scales or very high energy scales. Okay? Now, traditionally in particle physics, we've tried to uncover the theory of what happens when very small things bang into each other, how small things interact with each other by collider experiments. You take these huge colliders, you take particles, you bang them against each other, you surround them with detectors, you see what comes out, and then from that you try to figure out what the rules are for the interactions of these particles. Now, if you do a back-of-the-envelope calculation with some assumptions, but if you do a back-of-the-envelope calculation, you find that in order for quantum fluctuations of quantum gravity to be important for these collision, for the, to be significant for these, the outcome of these collision type experiments, we would need to collide particles at roughly what is called the Planck scale, which is an energy scale which is maybe 18 orders of magnitude higher than anything we've reached so far in colliders. 18 orders of magnitude, maybe 17 orders of magnitude is a huge energy scale. No collider experiment that is yet constructed, of course, or foreseen or is likely to be constructed in my lifetime will reach that energy scale. Okay, so we're not going to find out the details. I mean, unless we're somehow incredibly lucky and an unexpectedly lucky scenario plays out, we're not going to find out the details of quantum gravity, be able to probe the details of the theory of quantum gravity using collider-based experiments. Okay, perhaps we can look for clues somewhere else. As I've already said, we expect that it seems very likely, or very plausible at least, that quantum fluctuations were important in the early universe. So perhaps we could adopt the following strategy. Perhaps we could try, you see, if quantum fluctuations were important then they in some way have left their mark on the universe we see today. All we have to do to figure out what the details of those quantum fluctuations were is to back evolve the universe 13.6 and 13.8 billion years and sort of subtract out all the uninteresting stuff from this point of view that happened in those 13.8 billion years and go back, take the conditions we see now and use that to deduce what happened in the universe 13.8 billion years ago. But a lot has happened in the universe since then, right? We've had matter, ionized matter collapse into unionized matter. We've had galaxies form. We've had black holes form and collide. The sun has, zillions of stars have been born and so on. Lots has happened in the universe. So it clearly won't be very easy to subtract all that out and then use the observations that we see today to deduce what happened in the universe at very early times. Actually, some of this can be done quite remarkably in the context of this theory of inflation. Okay, for a very interesting reason about causality, some effects from the very early universe are not easily contaminated by what's happened in the universe since then and can sort of be read off. However, if you want lots of details of what happened in the very early universe, it won't be very easy to figure them out. It's possible in principle, maybe, but clearly it's not a very easy thing to do. Okay, so we tried collider experiments. Those were tough because it's hard to reach the required energies. We tried back calculating from what we see now to try to understand what quantum fluctuations were happening in the early universe. And maybe that will be possible one day, but it's not very easy. Perhaps we could search for regions in the universe where quantum fluctuations of gravity are naturally very large. Well, plausibly, there exist such regions. All of us know that black holes are now a study of experimental physics. LIGO finds a black hole every time, every week or so. Very often. And black holes exist. And our best understanding of the physics of black holes tells us that there's a region in the center of these black holes where space-time curvatures become very large. So perhaps what we could do is, when we get better at space travel, go near a black hole and probe the center of the black hole. Maybe that would give us experimental input into the nature of quantum fluctuations of space-time. But you see, this is not going to be easy either because of sort of conspiracy about black holes. Black holes tend to have these event horizons. And these event horizons are these one-way membranes. You can go into the event horizon very easily, but you can't come out. Not only can you not come out, you can't send information out, at least not very easily, not in the classical. So, if you were a very cruel advisor, you could imagine sending your PhD student with lots of equipment and send her into a black hole and say, find out what happens at the center of the black hole. And the student might be able to find out what happens, but she won't be able to publish her results. So you see, for perhaps related, perhaps distinct reasons, it's not easy to get, we've not easily been able to get direct experimental input into the details of quantum fluctuations of quantum gravity. Consequently, we're constrained to embark on our quest for the quantum theory of gravity with, at least today, with very limited guidance from experiment. This is the main reason, in my opinion, that we've done so badly so far in our search for the quantum theory of gravity. Okay, so now we seem to be in a bit of a fix. Our question, what is gravity, is very important. We need to know it plausibly in order to know the answer to the question, how did the universe begin? We're not ready to give that up. However, we don't know how to find this theory because we have no guidance, very limited guidance from experiments. So what do we do? Well, of course, there are many things many paths one could have adopted. One could have adopted this the strategy of postponing the question to later when we have more information. However, that's not how humans are, right? If there's an interesting question, we want to answer it now. We don't want to wait for 200 years. So what do? Okay. So what the community of string theorists has done is to adapt the strategy of the spherical cow. Now, some of you already know the story of the spherical cow, but let me recount it for those who don't. There was a farmer, let's say in Switzerland, who had a very productive milk cow. But one day the cow stopped producing milk. The farmer was very upset. It was a big loss. But luckily that farmer had a great physicist friend. Let's call this physicist friend Zhao. And the farmer went up to Zhao and said, "You're a genius. Surely you can come and tell me what I can do to fix the milk production of my cow." So Zhao goes up to the cow, looks at him and says, "Okay, to start with, let us model this cow as a sphere." At which point the farmer looks at a sphere, looks at the cow and says, "Thanks, Zhao. Thanks for your time. I'll see you later." Okay. So, what the story is meant to indicate is not just to be funny, but it's meant to outline a strategy that physicists often follow. What we often do, as you know, is to abstract, when you're faced with a very difficult problem, to abstract away the parts of the problem that seem essential, throw away the parts of the problem that seem inessential, and try to solve a simplified question that will hopefully contain the essence of the answer of the more complicated question, with the hope of one day getting back to the more complicated question. This is the strategy of the spherical cow. This is the strategy that string theorists have adopted. And I'm now going to describe to you in more detail precisely how we've adopted that strategy, what success we've had, what success remains, and so on. So, following the strategy of the spherical cow, we've stepped back from the ambition of finding the theory of quantum fluctuations in the universe that we live in. And we've asked a seemingly much simpler question. Let us try to understand in sufficient detail any one theory, or at least a class of theories, of quantum gravity. What do I mean by theories of quantum gravity? I mean theories which are quantum mechanical, and then in appropriate limits, low curvature, long wavelength limits, reduced to classical general relativity, interacting with well-behaved matter fields. Now, it has proved surprisingly difficult to construct even one non-trivial mathematically consistent model which has fluctuating quantum space-times. Okay. However, over the last 60 years or so, physicists have stumbled upon this incompletely understood framework called the string framework of remarkable power and beauty that we still understand incompletely and quite poorly. And using this framework, a then young Argentinian theorist named Maldacena was able to construct what, in my opinion, is the first fully satisfactory model of this sort about 20 years ago, a little more than 20 years ago, 23 years ago. Okay, I'm going to describe this construction to you in the next 10 minutes or so. But in order to appreciate the novelty of this construction, I'm going to first contrast this construction with a much more familiar construction. The construction of a simple quantum field theory called quantum electrodynamics. So let's take 2 minutes before we get back to constructing this theory of quantum space-time that Maldacena achieved 23 years ago. I'm going to take you back in history to an accomplishment, and also great accomplishment that happened much longer ago, maybe 70 years ago. A question that was posed soon after quantum mechanics was first invented was, how can we find the quantum theory of electrons interacting with the electromagnetic field? Quantum mechanics, when it was first invented, was applied to systems with a finite number of degrees of freedom. Quantum field theories, as we've understood, have an infinite number of degrees of freedom because they have a degree of freedom per point in space, and there's an infinite number of points in space. So the framework of quantum mechanics needed to be extended a bit to apply to such systems. So this question was interesting, was clear to the pioneers of quantum mechanics from about 100 years ago, most notably to Dirac, who sort of immediately started working on this question as soon as he felt he'd understood quantum mechanics well enough. Okay, it took a long time to get all the details straight. It took about 20 years to get all the details straight. But when it was all completed, the final theory that was developed, it's called quantum electrodynamics, had many bells and whistles that anyone studying quantum field theory goes through, renormalization and so on. But in the end, if you take away all the details and look at it sort of with a bird's eye view, that theory was very simple. You see, classical electrodynamics is a theory of electrons interacting with a classical electromagnetic field. Okay? And in quantum electrodynamics, the Maxwell part of the theory is upgraded in a rather simple way. In the quantum theory, there are quantum degrees of freedom corresponding to each classical degree of freedom. Okay? For each classical number, there was a quantum operator. There's a one-to-one correspondence between these operators and these numbers. And these operators and numbers went to each other by the Dirac correspondence principle. It's basically this X Poisson bracket P goes to I X commutator P is just generalized to this theory with some bells and whistles. Okay, so in the end, the theory of quantum electrodynamics was very closely followed very closely its classical counterpart. Had all the same structures as classical counterpart, same kind of one-to-one correspondence between degrees of freedom. Just the degrees of freedom that were classical became quantum. The end result of this construction, though it took a lot of work to get straight and make it predictive, was conceptually almost disappointing because it was so close to the classical counterpart. Okay, so now with this in mind, let me take you now to this construction of this one theory of a quantum theory of space-time by Maldacena about 23 years ago. Though, of course, he approached the question differently. You can paraphrase what he did, or one aspect of what he did, as follows. There is a theory of gravity, okay, which is far from the theory of gravity of our world. This theory of gravity is different from the theory of gravity in our world in many ways. One way it's different is that it lives in 10 space-time dimensions rather than 4 space-time dimensions. The 4 space-time dimensions we see about us in our world. Okay, this theory of gravity is called 2B supergravity. Okay, it's a name, and it's a very symmetrical kind of theory of gravity. It has a large symmetry group, something called supersymmetry. None of this really matters very much. Okay, so there is a solution to this theory of gravity in which the space-time takes the form of AdS5 times S5. Now, in this talk, I'm not going to tell you much about what AdS5 is. S5, all of you know, okay, right? S5. So all of you know that a 2-sphere is the locus of points that are unit distance away from the origin in 3-dimensional space. In the same way, a 5-sphere is the locus of points that are unit distance away from each other in a 6-dimensional Euclidean space. So 5 spheres is very easy to, well, if not exactly to visualize, but to understand. ADS5 is sort of a similarly symmetrical space. The one thing that you need to know about it is that it's not just space, it's space and time. It has 1 time dimension and 4 space dimensions. So there's some very symmetrical space solution, not flat space, but very symmetrical space solution of type 2b supergravity. Okay, and this solution is a solution which has a certain structure at infinity. There are many other solutions in this theory which have the same structure at infinity but change in finite regions. Okay, so Maldacena asked himself the question, what is the quantum theory of this type 2b supergravity with the boundary conditions of that it goes to ADS5 times S5? So that type 2b supergravity defined so that it becomes ADS5 times S5 far away, and then is fluctuations about that in finite regions. Now, if you were motivated by my example from history about the construction of the quantum theory of electrodynamics, you might have said, well, there will be various bells and whistles, but when you look at it from far away, from after some time, from a little bit away, you will realize that the answer will be just that for all the classical degrees of freedom of 2b supergravity, there's some quantum degrees of freedom, corresponding quantum degrees of freedom, which reduce to their classical counterparts. So there'll be some 10-dimensional theory with classical metric type operators and so on. And of course, this is the kind of thing that people first expected and people tried for various theories of gravity. It doesn't seem to work. Maldacena realized that there is at least one remarkable complete quantum formulation of this theory. His formulation of the theory was not given by 10-dimensional operators that were in one-to-one correspondence with their classical counterparts, as was the case for quantum electrodynamics. Instead, was given by a 4-dimensional quantum field theory. The 4-dimensional quantum field theory has a name. It's called UN n equals 4 d equals 4 super Yang-Mills. This name means something, but it's just some theory. This theory lives, in some sense, at the boundary of ADS5 plus S5, whatever that means. Now, if you've been listening carefully, you probably think what I just said makes no sense. I started this talk by talking about how quantum field theories are deficient because they do not contain in them what it takes to describe dynamical space-time. But in the previous transparency, I told you the quantization of gravity, 2b gravity on an asymptotically ADS5 times S5 space is a 4-dimensional quantum field theory, which by definition is non-gravitational, does not have fluctuating space-times in it. What sense can that make? The second thing that you might think is, well, this is a 10-dimensional space, and I'm telling you that the quantization of this 10-dimensional space is a 4-dimensional quantum field theory. What sense can that make? Okay, how does this make any sense at all? Well, I'm going to give you in 2 minutes some rough flavor of how it might make sense. You see, the one thing that I have not told you about, and that is important, is that this quantum field theory, UN n equals 4 d equals 4 super Yang-Mills, is a theory whose degrees of freedom are n cross n matrices. You remember I told you that a quantum field theory has one or a finite number of degrees of freedom at each point in space. Well, the finite number of degrees of freedom of this quantum field theory happen to be n cross n matrices. Now, this theory becomes reduces to the classical gravity theory. This Yang-Mills theory reduces this to this classical gravity theory in a limit, the limit where n becomes very large. Okay, so we've got a theory whose degrees of freedom are large matrices, very large, parametrically large matrices. Finite number of degrees of freedom, but barely finite. A very large number of degrees of freedom at each point in space. Now, people studying quantum field theories, and in fact, just studying integrals, have known for a long time that integrals, path integrals for quantum field theory, or just simple integrals, of theories involving when the variables in your integral are n cross n matrices become effectively classical at large n. What do I mean by that? You know, quantum mechanics is characterized by fluctuations of variables. Okay, there isn't a definite path. There's maybe a mean path, and there are fluctuations around it. In the limit that you've got a quantum field theory with n cross n matrices, and this n goes very large, for certain observables, trace type observables, these fluctuations become very small. And in these observables, the theory becomes therefore effectively classical because there are definite paths in space-time. So this has been known for a long time. This has been known from the time of 't Hooft in the early 1970s. Sorry, late 1970s. Now, so restated, you know, quantum theories have one very familiar classical limit. This limit, this is the limit we study when we first study quantum mechanics. It's the limit h bar goes to 0. It's the limit in which the correspondence principle works. It's the limit in which you can make quantum theories by taking classical Poisson brackets and upgrading them to quantum commutators. What I've just told you is that there is a second, in a certain class of quantum theories, there's a second kind of classical limit. A limit which is controlled not exactly by h bar going to 0, but by n going to infinity, the number of degrees of freedom in your quantum mechanical system going to infinity. This is the second kind of classical limit. This has been known for a long time, and yet has had rather limited uses. It's had rather limited uses for the following interesting reason. In the h bar goes to 0 classical limit of a quantum system, the classical theory you get in the h bar goes to 0 limit is very easy to understand. If you know what your quantum theory is, you know just by looking at the theory, what you get when you take h bar to 0. Just because there's a one-to-one correspondence in this limit between the quantum degrees of freedom and classical degrees of freedom. This new n goes to infinity limit, which is a new classical limit, is a more interesting classical limit. You can prove on general grounds that it becomes a classical limit. Things stop fluctuating very much. But it's very hard in a general system to know what the classical theory is that you go to in the large n limit. Okay? In toy examples, you can find it out, but not in general. Not in theories as interesting as n equals 4, d equals 4 super Yang-Mills theory. I think that physicists who've thought about this problem, for instance, for large NQCD, have always assumed that in reasonably interesting theories, this large N classical theory would be a mess. It would be some very highly non-local, complicated theory. What Maldacena discovered was that in the large N limit of this n equals 4 Yang-Mills theory, the classical theory that emerged was not some horrible non-local mess. In fact, it was the most beautiful classical equations ever written down by human beings, namely Einstein's equations of general relativity. Okay, but these Einstein equations did not live in a 4-dimensional spacetime. They lived in a 10-dimensional spacetime. These are the classical equations that somehow emerge from the theory in the large N limit. So what have I said? Okay, in the extreme large N limit, you get a classical theory. As N becomes a little bit away from being very large, you start seeing deviations from classicality. You see small quantum fluctuations. 1 by N controls these quantum fluctuations. But if N becomes finite, let's say N is 3 or N is 2, then these quantum fluctuations are totally crazy. And in fact, in this limit, there is no real sense in which there is a 10-dimensional spacetime at all. Remember, 10-dimensional spacetime came about in this quantum field theory as an approximation in the limit n goes to infinity. This approximation became a little worse when n was not quite infinity. So in the 1 by n expansion, there were fluctuations of the spacetime. At finite n, that approximation just goes away. It's not really there. So in this model, spacetime, the fluctuating spacetime, the gravitational spacetime, is not put in. It comes out. It comes out in this large n limit. It becomes a little more approximate when n is large, but not infinity. And so it just goes away at n equals 3. So if you want to put some words to this, you might say that in this model, the gravitational space-time was an illusion, by which I mean it was not a fundamental feature of the model, but some approximation that emerges in some limit and that goes away at finite end. I don't know if these words are appropriate, but they sort of sound deep and interesting. And the whole thing sounds fascinating. Okay, so this is what I've said. This model, therefore, there's a sense in which space-time is an illusion, an emergent notion, more precisely, that has precise meaning only at a very large n, but its reality becomes increasingly tenuous as n is decreased. Okay, so in the last 5 minutes or so of this talk, I will now reorganize our view of what we've just learned.
You still have 15 minutes, Shiraz.
Oh, 15 minutes, wonderful.
You don't have to rush.
Okay, great. So in the last 15 minutes of this talk, I will reorganize our view of what we've learned to see it from a different perspective. Okay. What we have seen, as I've tried to describe to you, is that the quantization of a particular theory of gravity, the theory of 2B supergravity in asymptotically AdS5 times S5 spacetimes, is a quantum field theory. This n equals 4 d equals 4 super Youngman's theory. And from a logical point of view, from the point of view of somebody who searches for a quantum theory of gravity, this is how you should see it. However, if you are a physicist who is not particularly interested in quantum gravity, can live without, trying to understand how general relativity and quantum field theory are put together, but are more interested in, let's say, strong coupling phenomena in a condensed matter system, or strong coupling phenomenon at LHC, in the strong interactions. Okay, you might think, okay, this is all very interesting, but it doesn't have very much to do with what I want to know. Very much want to do with what I do. However, there is a way of looking at what I've told you from the other point of view, from another point of view, that makes that statement not completely true. Okay, so there is a perhaps philosophically more mundane way of looking at this correspondence between, the quantization of gravity is the field theory, by looking at it from the other point of the other side. And the other side is this. Suppose I was a physicist whose interest was not in studying quantum gravity, but knowing about strong coupling behavior of this n equals 4, d equals 4 quantum field theory. This is some quantum field theory which is in principle very well understood. But as all of you know, quantum field theories may be extremely well defined in principle, but that's very different from knowing how they actually behave in practice. The limit in which this quantum field theory becomes simple kind of gravity, classical gravity in a big space, is a limit in which the quantum field theory itself is very strongly coupled. So you can turn around what we've learned and ask, can gravity teach you something that we couldn't easily learn, couldn't easily know about quantum field theory? Now that we know that this quantum field theory in the strong coupling large n regime is the quantization of gravity, perhaps we can use this and use the fact that we understand at least classical gravity or semi-classical gravity rather well to learn something new about the behavior of quantum field theory, at least this one particular quantum field. So what I'm going to do in the next 10 minutes or so is to describe to you, to try to explain to you that this is not an unreasonable expectation, and that it has already been put to work in several examples, 2 of which I will describe to you in some detail. Okay, so now we've changed our viewpoint. We're going to try to use this correspondence and try to use gravity to teach us about strong coupling behavior of quantum field theories. Okay, so I'm going to give you 2 examples about how we've already learned something which I hope you'll agree is interesting about quantum field theories, and then I will, My first example goes as follows. Look, on intuitive grounds, we expect every non-trivial quantum field theory at high enough energy densities to be described in the long wavelength limit by the equations of hydrodynamics. Okay, and the main idea that behind this expectation is that stuff equilibrates under the conditions I've described to you, under the high energy density and long wavelength limit. Locally, stuff equilibrates fast, but stuff can't equilibrate fast globally when that global space is big, because that takes time. That's limited by causality. So stuff equilibrates locally very fast, and then there is a dynamics that proceeds, that takes this locally equilibrated stuff to move towards global equilibration, and that dynamics is governed by equations of motion that are called hydrodynamics. Okay, so let me give you 2 minutes more about that. What is hydrodynamics? Well, the equations of hydrodynamics are the equations of the conservation of the energy, the stress energy tensor, and other charges, other charge currents. Okay, and these turn value of chemical potentials, or equivalently a local value of charge densities and local value of energy density. Okay, this is general intuition that has been around in some sense for 200 years. Okay, why do we expect such constitutive relations to exist? Why do we expect the stress tensor locally to be determined just by the parameters of local equilibration? Well, it's because stuff is locally equilibrated. Once stuff is locally equilibrated, it's characterized by its parameters of local equilibrium, which is local temperature and local chemical potential. Okay, now, so the theory of hydrodynamics, the sort of bottom-up theory of hydrodynamics that was developed by several people but sort of summarized by Landau and collaborators in the 1930s, is a theory that asks, what are the constraints that you have on general grounds on the form of the stress tensor and other charge currents as a function of the parameters of local equilibration. This was a question asked by physicists for relativistic hydrodynamics in the 1930s, and summarized in this textbook of Landau and Lifshitz on hydrodynamics. And the principle used by these people were general principles that should always be true. Using general arguments and general principles, they try to constrain the allowed constitutive relations, the allowed possible forms of the stress tensor and charge currents as a function of temperatures and chemical potentials. But you know, reasoning on general grounds without one example in front of you is a tricky business. It's often easy to get things wrong. Okay, and we'll see that that's what happened here. Now, 10 or 12 years ago, my collaborators and I decided to test this general expectation, following up on other people's work. The general expectation that things should locally equilibrate and be described by the equations of hydrodynamics and so on. In one example, that the gauge gravity correspondence is now opened out for us. We could ask this question for this particular theory, n equals 4, d equals 4 super Yang-Mills theory, by doing the calculations not in that field theory, but instead by doing the calculation in the gravitational theory, type 2b supergravity on ADS 5 It turned out to be possible to set up the differential equations, solve them in some way in the gravitational side. When all the dust settled down, turned out the answer was yes. The general expectations are largely correct. High energy density, long wavelength dynamics of this n equals 4, d equals 4 super Yang-Mills theory is governed by equations of hydrodynamics, relativistic versions of the Navier-Stokes equations. The equations of motion are the conservation of the stress tensor and charge currents. The stress tensor and the charge currents are determined in terms of temperatures and chemical potentials by constitutive relations. So far, general intuitive reasons working fabulously in this example. However, there was one catch. When you looked at the detailed forms of the constitutive relations that came out of concrete, specific gravitational computations, you found that they did not quite agree with the most general forms that Landau and friends had told us were allowed by general principles. Almost agreed, but not quite. There was some deviation. Now, this caused some confusion, and after a lot of detailed back and forth, Song and Soroka finally cleared it up. They demonstrated that the reason there was this mismatch was that Landau and Lifshitz had got their general, and Landau and collaborators, and summarized in the book by Landau and Lifshitz, got their general reasoning a little bit wrong, or they'd not been imaginative enough to account for all possibilities. When they identified the mistake in that reasoning and corrected it, and when they corrected it, they realized that not only were these new terms, the terms that didn't agree with the results that were suggested by Landau and friends, not only were these new terms allowed, in fact, in the kinds of theories we were studying, theories with certain kinds of anomalies, they were forced to be that. Okay? Okay, great. Now, why did I tell you the story in so much detail? Well, first, it's a story I like. But really, the story, I told you the story in so much detail to illustrate the kind of use that this gauge gravity theory correspondence has been put to in learning lessons about quantum field theory dynamics. At first, you might think the kind of use would be rather limited because, I've told you that there is this duality with n equals 4 Young's theory. This is a very particular theory. Very few experimentalists, if any, are interested in this theory. So even if you use gravity to learn all about this theory, who cares? But you see, life is not that straight. There are several claims about quantum field theory that take the following general form. All quantum field theories behave in such and such a manner. In some cases, the general claims have been asserted with good arguments, but without detailed checks. Gauge gravity duality allows us, in some cases, as in the example I've described to you, to subject these claims to detailed checks. And sometimes you find that the claims were not quite right. Not very surprising, because hard to get things completely right from very general reasoning. Okay? But once you identify what the mistake is, you can correct that general reasoning. And once you've corrected that general reasoning now applies not just to your one example, but to every quantum field theory in this particular case, including to QCD. In the LHC experiments or earlier experiments in Greek, QCD behaves like a fluid. And there are several indications that the QCD fluid has these new kinds of terms that were first discovered by studying gauge gravity duality. And in fact, it's forced to do so by some sort of anomalies. So you see, once you've understood the gauge gravity duality can be used as a laboratory, which allows you to test general claims in great detail in specific situations. When they're found wanting, you correct these general claims, and then these general claims apply much more widely than to the theory that you are able to study in detail by gauge gravity duality. This is one class of applications of gauge gravity duality as understanding strongly coupled quantum field theory, which has been useful. The next two slides I will explain another class that I was also interested in, which is of a different nature. This class goes as follows. In this case, it was not, what was learned was not a general lesson about all quantum field theories, but a particular lesson about specific quantum field theories. It often happens that, you see, I've described this gauge gravity duality, this correspondence between a gravity theory and a gauge theory, or the definition of a gravity theory from a gauge theory, in one particular context, namely that of n equals 4 Young's theory and this 2B supergravity. However, the general story is broader. There are many examples of this duality known. Now, something that always happens is the following. In situations in which you don't understand the gravitational theory very well, if situations in which you understand the quantum field theory side of the story very well, the gravitational side of the story becomes very complicated, and vice versa. Situations where the gravitational side is very easy to understand, very simple to analyze, the quantum field theory side is complicated. Now, there is one class of gauge gravity dualities which describe a kind of three-dimensional quantum field theories without even supersymmetry called matter-Chern-Simons theories. It doesn't matter what these are. Okay? These theories are relatively simple theories, much simpler than, in some sense, that I could make precise for you, but I won't try, than n equals 4 Yang-Mills theory. And correspondingly, the gravitational theory that describes them is much more complicated than Einstein's theory. In fact, the fields that live in this gravitational theory are not just the spin-2 field of Einstein, but massless higher spin fields for every spin from one to infinity. Okay, it's a very complicated gravitational theory. So complicated that it's not very useful to analyze that theory to try to understand more about the quantum field theory in detail. It's not so easy to analyze that gravitational theory. It's a very complicated cousin of Einstein's theory. However, even when a theory is not very easy to analyze in detail, you can sometimes see some structural features of this theory. And what was observed was the following. When you took one of these matter-Chern-Simons theories, which described bosons coupling to Chern-Simons theory, you got a particular bulk theory. And then you got the same bulk theory by studying fermions coupled to this Chern-Simons theory. This observation suggested, motivated the following conjecture. The conjecture was that bosons in 2 + 1 dimensions coupled to Chern-Simons theory are the same, are different, that there's a single fundamental reality, which is two different mathematical descriptions. On one side, bosons coupled to Chern-Simons theory. On the second side, fermions coupled to Chern-Simons theory. I know most of you don't know what Chern-Simons theory is. It doesn't matter, okay? It doesn't matter for what I'm saying. Okay. The main point is that this suggested that there are two different mathematical descriptions of the same fundamental reality in a non-supersymmetric theory, gauge theory in 2 + 1 dimensions. One side had only bosons, the other side had only fermions. Now, at first sight, this suggestion sounds absurd. See, bosons and fermions are irreducibly different in 4 and higher dimensions. For instance, fermions have half-integer spins and bosons have integer spins. Okay? However, when you look at this question carefully, you realize that this irreducible difference blurs out in 3 dimensions. They're not irreducibly different. And in fact, by now there's fabulous evidence, independent field theory evidence for this duality. This fact that apparently two different mathematical descriptions describe the same reality. One side, the description has only bosons, the other side, the description has only fermions. This is an interesting fact just about quantum field theory that was, at least historically, first suggested from this bulk analysis, and by now has had direct experimental impact, because this duality has played a role in a proposed new corrected description of the physics of the half-filled quantum Hall effect by condensed matter physicists. Okay. This duality, which at least in the first time it was proposed, had its origin in this esoteric gravity versus boundary duality. It's concrete enough to play a role in understanding quantum Hall systems in a lab. Okay, that's all I want to say about applied gravity. I know I'm sort of out of time, so let me rush through this. Several aspects of the story I've outlined above remain unsatisfactorily understood. To start with, the fact that our central quantum field theory, n equals 4, d equals 4 super Yang-Mills theory, reduces to 10-dimensional supergravity at large n, has been established only within the string theory framework. We lack a direct field theoretic understanding of this fact. In other words, we do not understand in detail precisely how space-time and fluctuating metrics emerge out of strongly coupled dynamics. It seems likely that we will learn many, many wonderful things by filling this gap. As I've described above, the formulation of a single non-trivial quantum theory of gravity, namely the theory of gravity on ADS 5 × S5, has been a non-trivial accomplishment that has yielded many surprising insights. For instance, the approximate nature of bulk space-time. The string framework asserts the existence of many more such theories. For instance, type 2b supergravity in flat space. In order to address it would be great to have the equivalent understanding of all these spacetimes. Moreover, in order to understand questions about the birth of our universe, in the end, we'd like a precise formulation of the quantum theory of gravity of our world, not just these spherical cow theories we've been studying. I emphasize that none of these are candidate quantum gravity theories of our world. Does the quantum theory of gravity of the real world lie within the string framework? If so, where? How do we identify and understand this theory? I don't know the answer to these questions, but I think it's likely that input from experiment, perhaps in some unanticipated manner, will eventually play a role in answering these questions. Okay, so that's it. That's my talk. I've tried to tell you that I've tried to motivate the study of quantum gravity for you by explaining that it seems likely that the theory of quantum gravity would be needed to understand the early universe. I told you about the string. I mentioned the string framework, which is an exciting but incompletely understood framework for quantum gravity theories of gravity. I explained how within the string framework we've found a complete and surprising formulation of a class of 10D quantum systems as lower dimensional non-gravitational theories. The result is a great surprise. There's a sense in which space-time are emergent notions in this model, sense in which space-time is an illusion. I explained to you how this correspondence can be viewed backwards in order to use gravity to learn lessons about non-gravitational theories, so that gravity becomes Einstein's equations by this route become a tool for studying quantum field theory dynamics. Okay, and finally, I explained to you that I mentioned that the complete formulation of other gravitational systems of gravity not in ADS spacetimes, is an outstanding formal challenge, and the formulation of the non-spherical quantum theory of gravity of the real world is an even bigger challenge. Thank you.
Thank you very much. Okay, so yeah, now we have time for questions. So Pasquale is already raised his hand. So yeah, please raise your hand, and I will in order. So Pasquale, you can unmute yourself and go ahead, ask your question.
Yes, thank you. Can you hear me?
Yes, I can hear you.
Okay. Well, first of all, thank you. It's a splendid talk. Thank you very much. Now, I have a couple of questions which are really non-specialistic questions. Actually, I have 3 questions. The first one is, can you comment, what is your take on other quantum gravity approaches, like, for example, loop quantum gravity, and in particular, the background independence of this theory, which refers really to the key message of general relativity, which is a background independent theory. And the second point is that I make the connection to loop quantum gravity when you mentioned it in the Maldacena conjecture. You mentioned that 10-dimensional space-time and gravity have disappeared. And in some sense, also in loop quantum gravity, you have a kind of disappearance of space-time. And the third, little bit more specialistic question is that you mentioned renormalization in quantum electrodynamics. And I wonder if you can comment on renormalization in quantum gravity theories also. So I'm sorry to put the 3 questions together, but I hope that you could.
Okay. They're all excellent questions. Let me try to address them one by one. Loop quantum gravity, I don't know very much about. However, you mentioned loop quantum gravity as you mentioned that one of the features of loop quantum gravity is that it is background independent as opposed to string theory. Well, I would sort of not completely agree with the second part. There is a sense in which string theory is rather background independent. For instance, in the one example of the quantum theory of gravity that I formulated for you, the only thing about the quantum gravity theory that is specified in its formulation is what happens to the space-time at asymptotic infinity. We sum over all spacetimes that are asymptotically ADS 5 cross S5. And then they're allowed to do everything they want to do in the middle. So while the asymptotic structure of space-time is fixed and is forced to be fixed because fluctuations of that asymptotic structure would involve infinite action. Okay? Inside, over finite regions, geometry is allowed to fluctuate as much as it wants to. So the formulation I described to you is, in my opinion, apart from this asymptotic structure, which is not a bug but a feature of this space-time physics, is completely background independent. There's more to say about this, but at least in my opinion, this is the situation. I'm not well enough. If part of the purpose of the question was to get my opinion on relative successes of loop quantum gravity and string theory, I'm not well enough informed in what the accomplishments are on the other side to try that. So I will pass on that. But I don't think that string theory, at least in the version that I've described to you, lacks background independence.
Okay, I understand.
Okay. Now, the second, could you remind me what the second question was?
Yeah, well, no, I connected to loop quantum gravity because of this disappearance of space-time and gravity.
Yes.
You mentioned it when n becomes large.
Yes.
That was a kind of connection I made, but you already replied somehow. Yes. Because that's connected to the background independence. I had a question about renormalization, which you mentioned in the framework of QED, and you can comment on that in quantum gravity theory.
Well, okay. So there are two kinds of renormalization. There's the renormalization that goes all the way to the UV. That is needed to take you all the way to the UV. That is needed in order to define a continuum quantum field theory in ordinary quantum field theories. That kind is not, at least as to the extent that we understand it at the moment, is not needed in string theory, because string theory does not have infinities. Okay, when you compute string loop diagrams, the part of the moduli space of a Feynman diagram that gives you infinities is in some sense cut out. So string theory does not need renormalization in that sense. There is a separate sense in which you might want to renormalize effectively to get some low energy quantum field theory. That works more or less the same way as always. But string theory does not need the renormalization that was needed to make sense of continuum quantum field theories, because just the size of the string sort of gives you an inbuilt UV cutoff in the theory, one that is not put in there for purposes of Wilsonian renormalization, not an artifact that is put in to simplify some equations, but is physical. It comes from the size of the string, at least in perturbative string theory. Okay, let me stop here. Please continue. Yes.
Thank you.
Okay, Marco, I think you're next.
Thanks. I would like to ask a question about the first part of the talk, so the first item in your summary. Could you please be kind of a bit more technical as to where exactly it goes wrong if we refuse to quantize gravity? Let's say I want to run the picture backwards and I have some Hamiltonian for the quantum fields. I run backwards, I compute the state earlier and earlier with the Hamiltonian evolution. At some point, maybe I can also use this hydrodynamic approximation. And then I just claim that the gravity should be determined. I mean, this is a coupled equation. Fine. I determine that gravity should be just fixed by the equation of by Einstein's equation, where on the right-hand side there is the expectation value for the stress tensor of the fields. I run backwards at some point. How is the theory telling us that this is wrong? And
if I understand you right, your question is, what is wrong by saying that? What is wrong with the conjecture that the theory is described by classical gravity interacting with quantum matter, and the right-hand side of Einstein's equations being given by the expectation value of the stress tensor? Is this a summary of your question?
Right. Yes. Thanks.
Okay. Excellent. I think you will run into logical contradictions if you try to do this. Let me remind you. Okay. Suppose you were to work with a double slit experiment. Okay. You have electrons that you shoot through a double slit experiment, and you have this phenomenon that when you don't look to see which slit the electrons go through, you see an interference pattern. But when you look to see which slit the electrons go through, that interference pattern is destroyed. You're familiar with this, of course. And this was very beautifully described in Feynman lectures on physics. Now, if you remember that description in Feynman lectures on physics, one of the things he did was to say, well, this sounds like it can't really work. This sounds like it's contradictory. Let's nail down that contradiction. So what he did was to try to see if he could figure out which slit the electron went through by shooting photons at the slit. Okay, and then if he could scatter a photon of shot at one of the two holes, he knew the electron went through this hole. But every time he did that, the interference pattern was destroyed. How was it consistent? It was consistent because the photon itself was quantum. So it carried a minimum amount of energy. So when it became small enough to be able to distinguish between the two slits, it carried enough momentum to kick the electron hard enough so it smeared out the interference pattern. Had the photon been classical rather than quantum, you would have been able to falsify quantum mechanics, because you would have been able to do this double slit experiment, make the wavelength of the photon small enough so that you could distinguish which slit the electron went through, but take the amplitude to be parametrically small, even smaller, so that the kick in that photon was so small that it couldn't disturb the interference pattern. Now, if you had gravity classical and everything else quantum, you could do this double slit experiment with the classical gravitons. Wouldn't be easy to do, but you could do it in principle. And you would land into a logical contradiction. So I think that it would just be a logically inconsistent theory. I've given you a picturesque example of how it would be, but I think you could pursue this more mathematically.
Thanks.
Shiraz, let me ask you, you sounded a bit pessimistic in your introduction, but let me ask you anyway. So do you expect any experimental hints from about quantum gravity from the, I mean, the next decades we're going to observe lots of gravitational waves and black hole mergers. Do you have any hope that we'll learn something from there, or everything will be good?
Do I have any hope that we learn something from primordial gravitational waves? Was that the question?
Well, I didn't distinguish either that or black hole mergers, whatever source.
Well, perhaps we could get lucky, but it doesn't sound very likely to me. You know, it could be we'll observe stuff like gravity waves from inflation. You know, there was this big burst of hope with the that turned out to be misplaced with the bicep experiment. Could be that something like that would happen, and that would be great, but it wouldn't give us very much information. Right? Something that is quantum gravity, and that gives us information, you know, not just one number, but a function or some detailed information about quantum gravity, seems to me to require a great deal of luck to happen. You know, when black holes merge, I think you'll see classical general relativity. Yeah, it sounds unlikely to me, though I would love to be wrong. But who knows, you know, as you know, Zhao, Polchinski at some point suggested that there might be these cosmic strings that we would observe. In certain compactifications of string theory, that would give us real information. You know, who knows what reality holds? But who knows? Who knows? I don't know. Yeah.
I don't see any other raised hands. I don't know if there are other questions. Otherwise, maybe I can ask you more generally. Well, I guess you already tried to answer the best you could, but I will press you again. So what about on the theoretical side? We did the spherical cow. So Maldacena proposed this, as you said, 23 years ago. So what do you see as the next big thing that we should try to achieve in this direction, or I don't know?
That we should try to achieve. Well, you know, my experience with the history of string theory has been this: that every time you decide this is what we should do, and we should use string theory to answer this question, you go nowhere. Okay. On the other hand, every time you listen to the theory, you do the calculations that it allows you to do, you follow the flow, you learn something you didn't expect to know. So I'm sorry, I'm copping out, Zhao, but I just don't know. And my advice to anyone who wants is not to put your preconceived biases on the theory, to do what you can, to follow the theory, to go with what's interesting, and you will be rewarded. That is what history has shown. Something beautiful lies there, but I don't know what it is. And I doubt the person who discovers it will know what it is until she discovers it.
Thank you. Okay, so I don't see any further questions. So let's thank again Shiraz for this wonderful talk. Thank you very much, Shiraz.
Thank you. Okay.
And well, I would like to invite you for dinner. So you
what's on the menu?
So you just have to take a flight whenever you can, and you will
Wonderful.
Okay.
Okay. Thank you very much, It was great fun. Thank you for the invitation.